Hello and welcome again to this lesson. Okay, so this is a concluding lesson, all right, part 4 of our model fitting and experimental modeling. Okay. So the first three parts, okay, we focus on the simple, okay, straightforward math model fitting. Okay, this time part 4 we are focusing on the what else, meaning that we are not dwell into the theoretical calculation behind that, okay, because this one is a little bit more extensive. You need to do your calculation on your own, okay, because this one is very technical, and at the same time you need to really use your um, machine, okay, on your own, okay. But right now I'm going to touch on a surface and the reason behind what you do afterwards, okay. So if you look at this one, okay, we actually focus on the other alternative about the more or less higher order polynomial. Okay, what if or else is not the same? Okay, what if we cannot produce just simple model fitting, least square fitting, for example? What if by the end of the day we need to really use a more complicated polynomial to address our data set. Okay, so earlier in our earlier part, actually we just focus on okay, even though it may not look simple, but it's actually a simple one term model previously. Okay, so previously it is a simple one term model, okay, that are able to capture your trend of the collected data. Okay, uh, okay, okay. What I want to say here is that um okay, it's like this. Since your data is since your model, the one that you construct your model is simple. Okay, their mathematical fundamental also simple. Okay, it's quite simple. Okay, so unfortunately, since it is simple, it is easy in a way, but unfortunately it is limited because it is simple, right? Because it is simple, so it limits you to capture your trend in a more appropriate way. What I mean trend in more appropriate way, for example, if let's say you have a situation where you only have like earlier we have exponential growth, that one is clear because it is exponential growth, okay, and then you transform your valuation, you get the linear line, and then okay, you are happy. And then by the end of the day, you transform again and you assimilate your your constructed model, the one with an exponent, and then you tie with your data, it fits just nicely. Okay, but what have ever happened if let's say your data is not like that? Normally your data is not like that. What can you do after this? Okay, what can you do? Um, how to move about? So this is the thing that we would like to consider here. Okay. The most common we use polynomial. Okay, this one actually polynomial is a multi-term. Earlier part we actually coined that term is a simple one-term model. But in this case right now we are start to focus on multi-term model. Normally we consider multi-term is a polynomial. Okay, why we are so passionate about polynomial? Okay, one, polynomial is easy to integrate. Okay, remember integration of your polynomial. Once you have a function, you can integrate easily, right? And remember what integration has to do with this. Okay, remember as long as your function is continuous and your function can be represented in a, time frame. Continuous, okay, you are able to see the summation. Okay, remember summation dealing with your blocks and blocks of your summation on your axis. Okay, that's why we tie back to the integration. All right, and then you can also easy to differentiate. Okay, meaning easy to differentiate. Let's say you have a absolute function. Okay, that's will give you a headache a little bit. Okay, isn't it? Because you have uh, a point that you need to reconsider. Okay, but polynomial is not so. Polynomial is just a degree. Okay, even though the degree is a little bit far off. For example, you have y equals to x to the power of 10 plus 2 to the power of x to the power of 9 plus 3 times x to the power of 8. Okay, even though it looks tricky, but it is still a simple function for you to integrate and differentiate, isn't it? As long as your x has the power, you don't have to realign your life and make your life miserable just for you to differentiate this particular model. Okay, why I said it is easier? Okay, because by the end of the day, no matter how much you differentiate this particular problem, as long as it is a polynomial, you can foresee that you differentiate, your power is reducing. Okay, you can expect this particular information earlier. Okay, it's just that the matter of how are you going to solve that. Okay, that's why it is popular. Okay, so that is the concept of this polynomial. All right. Okay, this is the example why people are so interested with the polynomial. Okay, if let's say you have a different dotted line, okay, a different dotted line, you can see over here, for example, in C, you can actually utilize as many polynomial as possible, join them together. For example, okay, that one you can look at it in a cubic spline. Nanti later I'm going to show you a little bit, touch a little bit about cubic spline. Why cubic spline is interesting, and people normally really utilize these particular issues. Okay, so these are the example. Okay, you can play around with the polynomial because of the structure, the way they function, the way the curve forms. Okay, it is not just like a only quadratic. Okay, but quadratic is also part of a polynomial, but that one is a low power. Okay, low power, but still, um, it is very easy for you to maneuver, isn't it? If you want a straight line, you can use a linear line, a linear function. A linear function is also a quadratic, isn't it? But the degree now is different. Okay, so that's why people are so pumped with a polynomial. Okay, so the higher the degree, you can see how it behaves. Okay. Okay, so these are I touched a little bit about the form of a polynomial. Okay, this may look like complicated information, but actually this is just to show you that given a sequence of pairs, okay, you can by the end of the day, you are able to find a polynomial degree such as this. This is the concept of the theorem. Okay, and then if you change a little bit the way we move forward. Okay, why we want to change it a little bit? Because we are more concerned about the behavior of the data set, right? Because we focus on the data set, right? Okay, so that's why if you notice we deal with this. Okay, but this is just because we want this. Okay, we want the what we call this, we want the relationship among the data set. Okay, that's why you can see x naught, x1 there, because if you transform your x is just in the sense of data, isn't it? Okay, so you can play around with this particular information. Okay, so try a little bit this one, but normally in the future, if you want to apply your knowledge on this, you can just simply use this per hand. Okay, don't actually necessarily need to know more about the fundamental unless if you want to construct the theoretical fundamental in this particular theorem. Other than that, if you just want to use this, please make sure that you know the basic knowledge. But what's important for you is to make this basic knowledge, put it into practice. Okay, here I'll show a little bit what are the advantage and disadvantages of a higher order polynomial, okay, compared to the previous one. Okay, as I mentioned earlier, easier for you to integrate and differentiate. And then it can be found that is able to represent most of the underlying behavior. Okay, but the problem, okay, this one is the most significant problem. For example, because when we are dealing with a polynomial form, we tend to have the oscillation problems. Okay, what is oscillation problem in the sense? Okay, I'll give you an example of this. If you have this kind of example, okay, unfortunately, you are dealing with a data of 000 and so on. Okay, if you look at the table 4.10, okay, with figure 412, okay, 412 figure representing your 410, but your 412, it's a fitting of a higher order polynomial through the particular table. Data in the table. Okay, you can see over here. What if you fit this particular polynomial with the available data that you have? The first few area is okay. What I mean, the first few area is okay. This one is okay. You get a stable information. But through here and through here, it starts to oscillate. Okay, it starts to oscillate. So this is the meaning of it. All right. So this is the meaning of this particular information. All right. So this problem, if you can see it, then that's fine. But let's say if you cannot see this particular problem involved, and then you don't notice that this actually this is actually what occur, then by right, you can see that actually on your xi, on the right side of your xi, you cannot actually believe with your results anymore, isn't it? So that is what's dangerous, okay, especially when it involves with a complicated information, okay, or a sensitive data. For example, you may find different results for your data if you blindfoldedly follow the higher order polynomial and you didn't check. Okay, so that's the example. Okay, okay. So, this one actually, that one is earlier higher order, but this one, we want to see. All right, we want to see whatever happened if, let's say, we start off with the low order polynomial first. Okay, what is smoothing? Okay, what is smoothing? Okay, smoothing mean you look at the figure 4.14. Okay, smoothing means you try to smooth the data. Okay, that's what it means by smooth the data. Okay, you don't need to um, you don't need to have a higher order of polynomial. You can smooth the data. You can only get a, for example, quadratic polynomial. Okay, the first one is in figure 4.14. The first one you have 9 order polynomial. The second one you have quadratic polynomial. Okay, quadratic is a low order polynomial, right? Because your n equals to 2. So you don't do much, uh, you don't play around much with the model anymore, right? Because your model is a little bit simpler. Okay, so that is, and are we able to choose the low order polynomial instead of choosing the higher order polynomial? Okay, so that is the aim. Okay, for example, over here, it mentioned here, aim find a method that retains the advantage of working with polynomial. Okay, meaning that polynomial is a little bit flexy, right, and versatile, but you eliminate the at this the advantage of higher order polynomial. For example, your issue with the oscillation problem, for example. Okay, so how you do just that? You do this technique smoothing. Okay, you choose a low order polynomial regardless of the number of the data point involved. Okay. Um, you decide which low order polynomial that best fits the data, and then you will achieve less oscillation and less sensitivity to the data. Okay, that is how we move forward to the smoothing. Okay, so there are another question that you need to raise. Okay, when you consider the use of low order polynomial, okay, uh, should a polynomial be used? Okay, and if that is so, what order of polynomial would be appropriate? How small is enough? How small is sufficient? Okay, so this is also lots of example. Okay, and then by trying to answer that particular question, okay, we move forward to the divided difference. Okay, this one, I really recommend you to keep on learning about divided difference. Okay, um, especially try match your problem with the example, because you can see through example why we use, okay, divided difference. What's the difference between the first difference, second difference, third difference, and you can see by mimicking the example, you can see, oh, this is what it means by your difference, your first difference, second difference changes, okay, according to the example that you look at. Okay, but anyway, let's forget about that at first. What is divided difference? Okay, so divided difference, the idea is that you use your earlier data. Okay, you use your set of data, and then you organize your set of data and find the difference. Okay, the difference actually, the idea is that you know, right, you just find the tangent actually. Okay, the concept is you find the tangent, but the concept of finding the tangent, meaning that you have the difference in distance, for example, on your y-axis, and then you have the distance, the changes in the changes in distance for your x, and then you divide them together. Okay, remember that one is actually your differentiation 101. Okay, your early knowledge on differentiation. Okay, but by the end of the day, okay, that's why this what we call this one, this is actually just your knowledge on differentiation actually. Okay, so by the end of the day, okay, if let's say these are the sets of data that you have one, two, three, four, five sets of data. So if you notice, you organize your five sets of data here: 0, 0, 2, 4, 4, 16, 6, 36, and 8, 64. And then this is getting interesting, how you construct your first difference. Okay, your first difference is you do exactly as how you do your this one. Okay, which is this one, as I said earlier, just the difference between your distance actually, isn't it? Sorry, x. Okay, the difference between your distance depending on your axis. Okay, so that's why if you notice, this is 4, kan, right? Okay, this 4 coming from 4 minus 0 divided by 2 minus 0, right? That's why you get 4 over there. What about this one? This one I give you two example so that you can follow later on. Okay, what about 12? 12 is actually 16 minus 4 divided by 4 minus 2. So that's why you get 12 over there. All right. Okay. So this is how you move. This is how you move forward. Okay. So the rest follows, and then the same thing happens for your the rest of your information. So you can imagine if let's say your data set is a lot. So you can imagine your difference table is also quite extensive, isn't it? Okay. So all right, if you look at the difference table, okay, you can see over here, careful in the judgment of what is small and what is not, the measuring unit, the relative qualitative judgment. The qualitative judgment is quite difficult a little bit to do because it deal with maturity in understanding what you have actually. Okay, so this is why I mean about trying to find another example. A very the better example is when your data is a lot. Okay, so you can see, for example, if you have one particular example problem whereby your first difference, okay, your first difference, you can see in one example your difference will increase indefinitely. By the end of the day it will increase straight, and then another example, your first difference okay, first it will increase and then up until certain point it will decrease. Okay, so if let's say that happens, for example, you have 15 data sets, all right, and then in the eight unit, okay, in the eight data set, suddenly instead of it's going increasing over time, and then later after eight, the nine data set, it will reduce, and it will reduce. Okay, so how you're going to judge this particular information? So that is the meaning of the qualitative judgment. Okay, that one needs a lot of practice and understanding of what is the meaning of your difference between this particular information. The same thing happens also, for example, up until when that your end of your difference, how many difference will give you the lowest valuation, meaning that actually by the end of the day, you can expect you will get zero. On your, let's say, 3, 4, or 5 difference, because difference is just like you differentiate your value, right? Because as I mentioned, it is just a tangent. It is just finding a tangent, right? So finding a tangent meaning that, oh, actually finding a tangent, the next one, your differentiation will reduce in power, and then the next one it will reduce in power, and then by the end of the day it will get a constant value, and then once you differentiate a constant value you will get zero. Okay, assuming that by the end of the day your difference table will end to the zero by right. But in a data set, we should expect that we may not get zero at all. Okay, because we are dealing with a data. We don't deal with an analytic assessment. But even though we are dealing with the data, a real data, by right, almost by the end of the day, we will get values that is nearing zero. Even though it may not get zero per se, but we should expect we get a very small value leading to zero. Okay, so you also need to be careful about the measurement errors. So what are these measurement errors? You can see over there, okay, in my these three information. Okay, knowing it by looking at an example is easier for you. Okay. Okay, so as I said earlier, okay, in this part, I just want to touch a little bit on what are available out there, okay, not on how you solve that. Okay, how you solve that is uh, another extensive information, okay, not captured in our syllabus anyway, and it's also sometimes tie with your other numerical analysis, for example, for you to move forward. Okay, so if you look at the higher order, for example, okay, higher order polynomial, um, okay, sometimes you use cubic spline. Okay, so what is this cubic spline? Okay, we use different cubic polynomial. Okay, what does it mean by we use different cubic polynomial between successive pairs of data point? Okay, the idea is that each data point, okay, each data point that we consider, if we segment, if we categorize, or if we segment the long data point that we have into few different parts of data point. For example, um, bite size data point. Okay, bite size data point, meaning that in each segment of data point that we consider, we uh, pinpoint them one polynomial. Okay, which is independent with another polynomial next to the segment, plus another independent polynomial next to another segment. Okay, you get what it means, right? Okay, the idea is, by doing this, you are able to capture the trend of the data. Okay, regardless of the nature of the underlying relationships. Mm. And then at the same time, you don't have problem with oscillation. Okay, because if you notice on the previous example, oscillation happens. You didn't notice. Sometimes it happens in the end of the prolonged strain of time. All right, when you leave it away, and then suddenly it will oscillate. Okay, but if you put your segment of different segment of data, okay, then your assessment to each segment is a short term only. Okay, so that is how we are able to do that. Okay, so I'll show you example of this, right? This is the complicated data set. Okay, data set that we have, for example, like this. And once you have this available data set, okay, you um, differentiate this segment of data set, and you represent your data set into different kind, okay, different valuation. So you can see over here you have S1 for that, S2 for that, S3 for that, okay, and then you have S4, S5. You have five different models for one particular data set. Interesting, isn't it? Okay, so this is the concept of a cubic spline model. But how you're going to solve this, I hope you learn um, on your own, because this one is also reflective of your numerical analysis. Okay, so these are the these are the conclusion. Okay, you examine the data. Okay, you once you discard all your outlier, you see whether your data is makes sense. All right, you see whether it has trend. Okay, if you are able to see, oh, the data trend is very clear. For example, if you have as exponent, for example, you build a simple single term, as in our part 1, 2, 3. You transform the data, you feed the model, you verify a little bit. But if you are not able to do just that, then you have no other choice. Okay, you use your polynomial. If um, you have very little data, see how it goes. If you have large data, see how it goes. Okay, if able, you should choose low order polynomial, easier for you. If not, then do whatever necessary, and then you can look at the cubic spline polynomial as well. Okay, so these are the concluding of what we do. All right, in a framework type of things, algorithm. That one, I think, just to simplify the things that you've learned so far. Okay, so I leave with this additional external video for you to also put through. improve a little bit on your model fitting and your experimental modeling. Okay, but I want to leave you with the concept of whatever it is that you have. Okay, whatever, as long as you have a data, okay, you are able to make some investigation on your data. Okay, so there is no such thing as you cannot analyze the data. All right, because we as a mathematician, for example, we really love data and we really want to understand our data more. And it by the end of the day, we would like to know the future, isn't it? Okay, who wouldn't like the future, right? It's just that the way we analyze the data, okay, and we concluding our remarks for the future assessment, should be based on a very objective assessment, and make sure that um, you also need to know, okay, you also need to know your limitation of the data. Okay, why? Because if let's say you have give appropriate assessment, or you forecast your future data, for example, okay, you have to understand sometimes people just want the numbers and people don't care how you derive to the numbers. Okay, so sometimes they use your projected data without even thinking, okay, and without even further analyzing whether that is the correct assumption or not. Okay, so that's why you need to really scrutinize on how you assess your data and get the final decision, so that people would not do that for you. So it is some sort of like an accountability lies with you. Okay, you analyze the data, so you are responsible to see the discrepancy of your data, or you are also responsible to be honest with your data, whether your data is a correct data, or whether your assessment or your forecasting process or your projection is based on the thing that you believe in. Okay, it is better to have a not so good model, but you know which part is a little bit shaky, okay, rather than you bombastically believe in your projection, but actually your data is lousy, or let's say you didn't give much thought about coming back to your original data and see whether your projection fits with your original data. Okay, meaning that whatever thing that you do, make sure that it is not just your result just not because you want to have a very good and your result look good on paper. No, that is not your main intention. Your main intention is to make sure that whatever the projection valuation that you do using your sound analysis is because of a strong fundamental support decision making. Okay, so I really need to emphasize that, all right, because in the world out there, you need to understand that people don't care much about the analysis, the way you analyze things. Okay, they just care about the findings. So your assessment must be sound, meaning that the accountability, okay, the accountability part must be lies on you. Okay, so I hope you get what I want to highlight, and I hope you get the benefit from the rest of my video, this video, and also for the rest of the mathematical modeling playlist. You are free to visit this playlist again and again and find benefit with this, hopefully. All right, so all the best, and I hope you don't stop learning until you die. Okay, so enjoy the video. Assalamualaikum.